Hello, we are back and gonna continue, to review your all knowledge about order differential equation. And this part we gonna extend our previous the knowledge you learned from our previous clip, to extend it to what we call the higher order linear differential equation. Okay, I think that. To simplify the concept, of the linear differential equation to a lump system, we already defined the definition of the lump system for you, that the coefficients that multiply for each term of derivative in all kind of order, start from zero order up to n order in this one, okay, is just a constant, it's not the function of domain that you are interested. So the function domain of the that you consider in the equation will be on the right hand side. Okay, and we have seen at least one mechanical system and one electrical system. Okay, that can be formulated as this type of differential equation. Okay, and you know that the solution of the general solution of the differential equation, for y of x, uh, it depend on the order number involved in the equation. Okay, suppose n is the largest, n is the largest order in the equation. Okay, therefore you need an initial condition, boundary condition, that equal to the number of this highest order. Okay, and for example here, if you have from this in general form that you see on the screen, if you consider initial condition, you need y of 0, first order derivative as evaluated as 0, and second order, and so on up to the n minus 1 order. You don't need an at the order n, because you only need only n condition. Okay, because this n condition will help you to find the constant that will appear on your complementary solution of y. Okay, the same can be applied for boundary condition, but for boundary condition, since you add one more parameter at the terminated part of the domain, for example, the time domain, you terminate at capital T. Okay, so you need both zero order, so there will be two conditions for zero order, two conditions for first order. Okay, you can add it up until you reach the n condition also. Okay, uh, so we're gonna move on and trying to apply the previous knowledge that we learned from the previous two clips, to solve this following example. Okay, we're gonna move on to this one. Is this look familiar to you? This problem? I think it's very familiar because it's contained in one of the problem. Okay, on page 18 here. Okay. This is the problem that we talk about as part of homework. Okay, but we're gonna try to illustrate how to solve this type of solution for you. Okay, and also you might recognize this one. This is second order mechanical system. Okay, we're trying to, help you, with the upcoming example for you, that to get a clearer view, and then you can go back and working on those homework problems. Okay, for this one, this is a little bit more complicated alternate current circuit. And you know that there exist the number of there are two resistor, two inductor and one capacitor here. Okay, and we are interested to find what is the current function over time for a given dynamic input voltage over time ET. Okay, so this one is we can apply and use the previous concept from the last example of the example one. You remember that the electrical engineer no the electrical circuit problem. Uh, but this one is a mechanical problem, okay? But we're gonna move on to from example three. You can, if you might remember from example three, okay? Okay, but we in this one, okay, we want to study the concept of current here, okay? The I is a function of t, okay? It's from the easiest concept of Ohm's law, okay? The function of I with respect to t will be equal to the ET, the input voltage, okay, over time divided by this one. We call the impedance, okay, across the pole AB here, okay. And if we be able to find the impedance across pole AB here, okay. So, and we can substitute it to this formula. We'll be able to find the relationship between the current and the voltage here. Okay. Next, we want to find the whole resistance across, okay, this terminal A and terminal B here. Okay. 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 Look at here that we have R sub 1, okay, resistor, and connected in series with okay, look at this to this part, okay, of the problem. Okay, we have L sub 1, okay, one inductors connected in series, okay, with a capacitor, and they connected parallelly with uh, another inductor. Okay, this is the second part. The third part is that this first part is R1, second part is this one, and the third part that all connected in series is another resistor R2. So C across terminal AB here, okay, okay, the impedance across here will be equal to R1, okay, in series, okay, when you have a resistor connected in series, you just add it up together. Plus, okay, this two is what we call the parallel, okay, connected in parallel. But the one part is have two electrical element, okay, connected in series, okay, which is this one, okay. In this one, you from the previous one you can know that the impedance across the inductance is D times L, okay. You might remember D times the parameter of the inductors, okay. D times L, while D is equal to D by dt, and the impedance across a capacitor from the example 3, you know that is 1 over dc, okay. Actually it's integrate 1 over c integration it dt, I the cross here, but the current that passing out sub 1 and c is separated by into two parts by the incoming it at this point, okay. They're separate into have two current, okay, runs in parallel each other and then reconnected at this point, and then the same it here, okay, passing to the resistor, the second resistor here to reach terminal B. Okay, so you can see that R1 and R2 are connected in series, so this one. But in the middle form, okay, is this one is L in series with C, which is the total impedance. It will look like this: D L sub 1 plus 1 over D and C. Okay, this is all plus is because they connected in series. But this two is connected in parallel with L sub 2 here. And you might remember the when you have two impedance connected in parallel, okay, you're using the impedance of both part, okay, multiply together and divided by the summation of uh, impedance for each part that connected in parallel. So this is what we did here. Okay, okay, the the one that connected in parallel with L2 is L1 in series with C, which is you have an impedance of D times L sub 1 plus 1 over DC here. That's the impedance above here. And then multiply to this one, the one that they connected in parallel, which is DL2. Okay, DL sub 2 is the impedance of here. Okay, you might recall that D can be is a replacement of d by dt or maybe j omega. Okay, where j is equal to square root minus 1. Okay, so this one is multiplied to each other. Okay, and then divided by okay the summation of impedance of both parts. The first part is this one dl1 plus 1 over dc, and then the second one is dl2. Okay, so this is the middle term here is or the second term of this summation. Okay, it belong to the total impedance here connected in parallel. Okay, and then we just rearrange the term. Okay, you can see that you can multiply d times c. Okay, from in both part, okay, of the fraction. Okay, so up above, okay, you get d times c, okay, and divided by d times c, okay, and what d times c multiply uh, in this part is become d square L sub 2 here, okay, L2C, okay, because we multiply, and d become d square. This lead to the second order also. And then, okay, the bracket in here, okay, still the same. And then on the second part here, okay, of the fraction, okay, you get d, okay, dc, okay, just cancel this, okay, so this you get the term of plus 1 here. Okay, but this one dl1 plus dl2 you can connect them together to become d, okay, and you have bracket of l1 plus l2, and then since you have dc multiply the whole term, okay, you can have dc d become d square and c. Okay, previously you have only d, right, and then d square c, and then with a bracket of l sub 1 plus l sub 2 plus 1. Okay, next we just rearrange the term. Okay, you have another fraction here. Okay, just separate, just multiply this term to both r1 plus r2. Okay, you use r1 plus r2 multiply all this term. Okay, and then plus okay here, okay, to be this part of fraction, and then divided by this one, and then you rearrange the term again. Okay, resulting to here. Okay, I'm not gonna explain much to here. I think that you can track it out by yourself. Okay, it's a very simple algebra. Okay, and after this you can see the after I rearrange the term, you saw this the side of d to the 3 here. Okay, or it become the cubic function of the d operator. Okay, so you would know for sure when you substitute impedance across terminal AB, okay, here, divided here, or you move C of AB multiplied to IT here, equal to ET, okay, to illustrate the Ohm's law, okay, you get this, okay, and it become the resulting differential equation become the third order system, okay, because uh, they have the term of the third order, okay, of the function that you want to solve, okay, and in the equation, okay. You can see that the right hand side is not just a function, it become another the differential function also, okay, because of this denominator here, okay? When you multiply CAB, this part, okay, sorry, this part, okay, of the fraction is belong to the left hand side of equation, okay, when you move here, okay, because this part when you divide it to here, when you move to this side, okay, it's multiplied to IT, the function IT here, resulting to this left hand side. But this part of the fraction, okay, you don't move to multiply, you just move it up, okay, to multiply to ET. Okay, according to the division law, this resulting is d square become second order of ET, okay, and then plus 1 here become ET here, okay. So this is a resulting what we call the third order equation. So when you have reached the third order system here, okay, you need to have 3 initial conditions here. So we're going to assume that you have I evaluated at time 0 equal to the first order of I, okay, evaluated at time 0 equal to the second order of I evaluated at 0. And why we set up like this? So it's the same logic that we used before, that we're using on-off switch at time t is equal to t is equal to 0 on this circuit, okay. And you need 3 because you know that your characteristic equation here, okay, characteristic equation consider only the left hand side of the equation in the differential equation, and you can see that you can write this because you're replacing the derivative term in according to the order. Like if you substitute uh, di by t by dt as s, okay, here s, okay, so it's become this one, and you say I would say that suppose that the term in the bracket that multiply to the third order derivative here is a, okay, and this one is for b here, okay, this bracket that multiply to the second order derivative is b, and c here, okay, the for the first order, and then for the zero order here, okay, it become your characteristic equation become the cubic equation. So you need to find the root of this cubic equation. But you might wonder, we discussed a little bit that how do we find the root of the cubic equation? Okay, I think that you can easily search, okay, in the uh, Google here, okay. Suppose I would say the cubic equation, okay. I type a cubic equation. So this one you have Wikipedia cubic equation. Yeah, this is a similar form, right? Ax to the 3 plus bx to the 2 plus c times x times plus d equal to 0. It's the same. We just replace x by s here, okay? The same type of equation. And you might know that from the second order, we can apply the classic formula for the root of the quadratic function, right? But we rarely see the general form for the root of the cubic equation, okay. That's very and there's a reason why, because if you go through this information on Wikipedia, you're going to end up having if you want to justify this is all the derivation idea and history of solving this. But if you want the to find the real formula here, okay, the general formula, okay, they'll be starting with Cardano formula here, okay, but Cardano formula is not quite a complete cubic form, okay, but for general, that's a historical development, okay, but for the general form here is start here. You go to first you search by Google, and then if you want just to want to find the formula, you're not interested in the derivation, you move down here, okay, and take a look at the topic we call the general cubic formula here. The general cubic formula is like here, that if you have this the root of polynomial here, but you want to find x here, you need to compute delta sub 0, delta sub 1. because you know the value of A, B, C, and D here. Delta 0 and delta 1. And then you find the capital C according to this formula. It becomes the root, the third root here, okay. Once you find C, you'll be able to find X, okay, and in general form, XK, K0, 1, 2, which means that you have three root here, is in the formula like this, okay. By replacing, if K is 0 is one of the root, K is equal to 1, another one, K is equal to 2 is another one. So this is a general formula for the root of the cubic equation, okay. And I'm not gonna there are many conditions here, okay. You might remember when we analyze the quadratic equation, we can analyze several type of three types of outcome for the or possible type of root of the quadratic equation. Remember that you have both as a real root, and both one of them and both are reals and also repeated root or distinct root, or the third one is we have a complex conjugate. Okay, in this one also you have, once you have three root here, okay, I mean you can apply here, I mean, okay, and you know the condition here already. It mean that you have an exact formula that you can find here, okay. You use the to solve it. But once you get the result of three roots of S here, okay, from this auxiliary equation or characteristic equation, there are four types of outcome can happen. Okay, consider here. First one, you have all real roots. Okay, all roots are a real number and have a different number, distinct to each other, distinct root. Okay. The second choice is that we have a pair of repeated root, okay, and but the third root also the real root have to be real because only one left, okay. Okay, but the first two is a real S1, S2 is still a real root, but there exists a pair of them that have a equal S sub 0, okay, which is different from the last one, the third root. The third condition is that, okay, you have all three root, okay, the same number, S sub 0. No, all equal roots, okay, three of them are all equal, okay. And the fourth case, you can easily guess that is, okay, there exists one real root, okay, S sub 1 here, but the other two root it is in the form of complex conjugate. In this type, I'm using P plus minus J times Q, where P and Q is a real number. Okay, so you can see that with higher order system, okay, not only you need more condition in both initial and boundary condition, depend on problem that you're trying to do. Okay, for the, you remember that we solving characteristic equation for what? For solving complementary solution. Okay. So the higher order differential equation become, okay, more scenario, okay, that can happen for the type of complementary solution you need to analyze. Okay, in this one we have four cases here. Okay, we're going to continue to look at each case here. Okay. First case, when you have S1 is a real number, not equal to S2, not equal to S3. So the general formula is quite clear. It's all three exponent functions, okay, with constant multiply with the each of the root times the domain t here as a exponential power here. Okay, so this I complementary solution in case one. Case one is that all distinct real root. Okay, you have c sub 1 times e to the s sub 1 times t plus c sub 2 e to the s 2 times t and plus c sub 3 times e to the s sub 3 times t. Okay, but in case 2 is that you have one equal root, which distinct from the last one. Okay, in this one, suppose that s0 is those is the two root that are equal. Okay, so when you have equal root, okay, from example 3, you know that it's gonna be like c sub 1 e to the s sub 0 times t. But the second term, once you have the same root, okay, you need to add domain with the constant here, c sub 2 times domain t times e to the s2 times t. And the third one, S3, which is another distinct root. Okay, you just use similar thing that you did on case 1. Okay, and but for case 3, you can see that all the same root. Okay, all three root is the same number as C sub 0. So you just extend the idea that you remember that if you have two real root, you extend to C1 and C sub 2 times T. Okay, if you have three same root, okay, you just expand another term, but this one become another constant times t square. Okay, if you have fourth order, fourth distinctive, four equal root, okay, we can add c times 4t to the third, e times e to the s sub 0 times t also, and go on. Okay, so this is a type of the third case. Okay, c sub 1, c sub 2, c sub 3. And also the fourth case here, fourth case is just combination. You know the latter part here, okay, from the example 3. This is a format when you have a complex conjugate root. And then the first one is that since you have another one have to be real root, okay. Okay, so this is the, so that's what I mean that when you analyze higher order here, there will be more combination of the type of root that can happen. Okay, the pattern of the root that can happen, and each case, okay, leading to different type of complementary solution here. Okay, and you can see that for all of them, okay, there exist three constants, c sub 1, c sub 2, c sub 3. That's why you need three, either initial and boundary condition here. Okay, and then we move on to take a look at the particular solution here. Okay, IPT. Okay, certainly the current function over time, okay, equal to the current function according to complementary solution or transient solution plus the current function over time for the particular or the steady state solution. We will go back to the original third order differential equation system here. You have A times third order of I corresponding to T plus B times second order of I, and then C times first order of I plus D times zero order of I equal to, okay, G, okay, another parameter, times second order of E plus uh, the input function e as a function of t itself. Okay, and this one is written from the derivation here. Okay, okay, where you can matching the coefficient that like you know what is the a b c d. Okay, and e is a input function, and a b c d on the left hand side, and g and h. G, okay, you don't have any h because et times a constant of 1. Okay, so you can know the a b c d, okay, and g here. Okay, this one, a new definition of c times summation of l sub 1 plus l sub 2, which is appear here. Okay, this one, c times summation of l sub 1 plus l sub 2. Okay, this one just make to simplify the notation before further derivation. Okay, if you put all the term here, okay, the equation will keep complex. Okay, so there are some other ways that you simplify by assuming it as a new variable to make the equation a little bit more not too it can have a better view, better look at the equation rather than see very long and many parameters involved in equation. And also we're gonna analyze the I sub pt, particular solution of current over time, okay, by considering this type of formula of ET. Suppose your input function of voltage function across the here, okay, across the terminal AB here, okay, is in this form. Is a summation j equal 1 to m of the amplitude of A sub j times cos of omega j times t, and then plus another amplitude of B sub j times sine omega j times t. Is a additive sinusoidal function with different type of frequency of omega j equal 1 to m, and where each of them they have both sine and cos sinusoidal function. Okay, for the cos function the amplitude is A sub j, for the sine function the amplitude is B sub j. Okay, and you can see that when you trying to apply the coefficient comparison from left hand side and right hand side, you need to first of all evaluate, okay, the type of the right hand side first, because mostly the right hand side we already assume it as something, a function that relies on some domain. But in this one, since the right hand side also contains some derivative of the input function function e, which corresponding to domain t, okay, so we need to rewrite this in general form first, okay, and since et here is in this form, okay, in order to clearly illustrate what the function on the right hand side look like, we need to find the second order of e over t, okay. So this is the first order, okay. Okay, the first order you can easily using the basic calculus that, okay, this one we find the derivative of e over t, and since e this function and a sub j and b sub j is a constant, okay, with omega j is and also a constant, okay, for all j. So it rely on domain t, okay. So the first order is only that when you're trying to find derivative of cos, you get a minus sign here, okay. And then since this is the cos of the some some constant time the domain, so you need to take another derivative within the cos of the angle of the cos, okay, and the derivative of omega j time t over t is omega j. So you have omega j time moving out here and multiply to a sub j, and you have minus sign because your derivative of cos is minus sign. And the same we analyze the second term here. You find derivative of sine, you get cos plus, no, it's not minus. And certainly you have b sub j here, but omega sub j is happen when you can know that when you find derivative of sine, you need to find another derivative of the angle of sine also. This is this one. When you find derivative of sine, you get cos, and then you find derivative of its angle is that over t is omega j. So that's why it appear omega j here. Okay, with similar spirit, you can easily to show that for the second order of ET, you know that you find derivative of another sign, you get cos. The minus sign is still there because the derivative of sign doesn't give any change of the sign. And but the omega j become omega j square because when you find derivative of the angle again, the omega j coming out and then multiply the previous coefficient here. And also the second term here, when you find the second derivative, and you're gonna cos the sign plus here because when you find derivative of cos become minus sign, that's minus here. And the same as the first term, when you find derivative of cos, you get sine, and then this one become omega j squared because when you find derivative of the angle inside over the domain, you get another constant omega j to multiply the uh, the previous coefficient from the first order, okay. So this is the resulting, okay, the last line we're gonna put here, okay. You can see that it's quite, because it's a sinusoidal function, no matter how you find the derivative, you can, Either you have cos, you find derivative, it becomes sine. You have sine, you find derivative, it becomes cos. So the type of function doesn't change. Okay, it's still but just the sign, the direction is different, and the amount of amplitude. Okay, but in this second one is a in general form, but it doesn't cause any change of your IPT. Okay, because your IPT will follow exactly what the second order here. Okay, but your second order need to multiply to need to add up with the origin of ET here. So let's see how it go. Okay, so we combine these two terms. But you remember that the second this is the right hand side evaluation. We You have to make sure that this is the right hand side. Okay, for the second order of E over T, you have constant G, okay, to multiply. And then you after this multiplication, you use this term to add it up to the current, yeah, function of ET, okay? So this one is already the rearranged term. Okay, actually how you're going to do it is that I'm going to use G to multiply the last line here. And then I'm going to add it up with the first line here. The first line just multiply by 1. Okay. So it's obvious that, okay, you can see that the cos sign is a common term. But for the amplitude for this cos is that for ET is still A sub j. But for G times second derivative become minus G times this value, omega j square, omega sub j square times A sub j. And you can see that the cos function become like this. Okay, one is from the ET function alone. Okay, in this one, but this one is that minus coming from here, this minus sign. Okay, since you add it up together, this side is just show the minus, and it become G. G is a parameter that multiply here. Okay, so G multiply this whole term. And then you can find that you have omega squared j squared. Okay, and all this term, okay, you need multiplication with aj here. Okay, okay. Since because the first term you have a sub j here, the second term you also have a sub j here. So you can pull, okay, a sub j out here, and this is become the new coefficient for the cos omega jt. And the similar fashion is for the second term, this one is for, because it just change from cos to sine. Okay, but for to sine is a little bit it's the same as that, because in terms of ET all they have all positive sign, but the second for the second order become all negative sign. So that's why you get a similar one, but just change from a sub j to b sub j here, and change cos from sine. Okay, and to simplify this one, I'm going to replace this one, the new amplitude for cos omega j here, as a star j, and b star j is the new amplitude for this sinusoidal sine omega jt here. Okay, so now you know the form. I mean that the form of the right hand side become summation j equal 1 to m a star j, okay, cos omega j times t, okay, cos omega j times t, plus b star j times, okay, sine omega j times t. Okay, so that leads us to very easy ways to consider. So what type of I sub pt gonna look like? Okay, particular solution of current over time. Certainly gonna follow the same format as the right hand side of the differential equation. Since in general form j equal 1 to m of cos something the amplitude of a cos omega j t, and the amplitude times sine omega j t. So the type of output gonna look the same, but the difference is that it's gonna be another unknown that you have to find by comparing coefficient. Like certainly they're gonna the IPT, the particular solution gonna contain the additive of m form of sinusoidal of cos omega jt and sine omega jt. but the difference is the amplitude of IPT. Okay, the first term here is we're gonna set up as a u sub j. The second one that belong to the cos sinusoidal function, but for the sine sinusoidal function we're going to use v sub j here. And certainly when you're trying to, well, once you get the form of particular solution here, okay, let me remind you again, this form particular solution, you'll be able to define like this because you already evaluate the type of function of the right hand side of the equation here. Okay, this one, the GE second order of B plus CT, and then once in this one, you already evaluate and you know the type of the right hand side. That's why you setting up, you'll be able to identify the type of particular solution here. But next, okay, this one we already did on the right hand side. Okay, next we're gonna look on the left hand side. Okay, for the left hand side, okay, you can it's a little bit more complicated because on the left hand side you have both zero order, first order, second order, and third order. Okay, multiply to each of them have a coefficient that multiply. Okay, and you need based on this substitution, okay, you need to find the general form for first order of IPTI, second order and third order of particular solution. Okay, so when once your particular solution be able to identify like this, you very similar for the solution that you did with function of ET here. Okay, we're gonna find the first order. Okay, similar way, but just a different notation. This one become omega j uj sine omega j, and this one dip cos you get minus, dip sine you get plus cos. Okay, and then we go to the second order. Second order, so the first, second, and third order just follow the same type we analyze here for ET. Just apply to for the I here. You get both minus psi, and then you need another derivative with the third order. Look how the third order gonna look like. You get cos here, and then you find derivative of cos. You get minus psi, and minus times minus here. You make this to become a positive again. Okay, and the omega j start to increase this third order. Okay, once you find the derivative inside again, you get another omega j multiply the previous value, but u sub j still keep in there. And then this one, even though you have minus, but the minus sign still maintained because when you find derivative of sine, you get cos again. And again, you from omega j from third order become omega j to the third. Okay, so this is a general now. Okay, now you are ready. You have third order term, second order term, first order term, and zero order term. So you are now ready to use all this and substitute to this equation. Okay, remember this equation coming from? Coming from this formulation. Okay, this is a resulting of formulation, and you want to simplify it by assuming the new parameter, okay, that related to the system component parameter. Okay, so in this one, okay, we're gonna try to rearrange the term again for the left hand side. Okay, for the left hand side, this one I already simplified for you. That we all know that doesn't matter how high order you're gonna get sine, cos, cos, sine, okay, alternate each other up to the infinite order, okay. So in this one, you know that the right hand side is in the form of cos and sine here, okay, the summation of cos and sine. The left hand side gonna end up the same, but you remember that you have for each uh, derivative term, you have a constant multiply a, b, c, d, and so on. So you need to add this, okay, for each substitution of I function of I particular solution over t, okay. So like a is always a multiplication for the substitution of third order, okay, of it, okay, of function it. Okay, b is for the second order, c the first order, d for the zero order. Okay, and that's what we did here. Okay, you can see that if you have cos, okay, in terms of cos, the third order here, okay, you get minus for cos, you get minus first, but you know that for third order you always have this multiplication of a. So this is the result that a times minus here, okay, this is the first, And then you move on to second order. Second order, the cos sign is also still maintain the negative. But you know that in the equation you have b multiply this second order term. So that's why you get minus b here. And omega j square uj is here. Become the cos. Now you have v sub j, u sub j. Okay, here. Okay. And for first order, you another cos term here become, and this is a positive sign, but you know that you need parameter c to multiply. And the last one is multiple for cos is the parameter d, and only u sub j. Okay, no omega j because it's in the zero order. That's how I come up with this type of coefficient that all added up and multiply to cos omega jt for each j equal 1 to m, and you sum it all together. The same logic for the sine term. Okay, for the third order, the sine term positive sign, right? But you need a multiply this amplitude here. And then for b still minus here. Okay, so the same as in the cos term. For the first order here, okay, for the sine become negative. Okay, sine alternate sign from the cos or in the first order, and then in zero order the same. Okay, so now you can see that you have a general form here. Okay, but you're trying to find that what is u sub j value and v sub j value. Okay, for a given you can see that for a given the right hand side here. And right hand side, you know g, you know omega j, you know a sub j, you know b sub j is a input function from here. That if you have the input voltage in this one, it means that you already know the value of a sub j, omega sub j, and b sub j. Okay. And for each parameter a, b, c, d, or g here are all rely on the system component value of both R sub 1, R sub 2, L sub 1, L sub 2, and C. Okay? So once you already know this, you can start to apply what we call the coefficient comparison. Okay? Let's go. How do I come up with this equation for AJ? I'm going to use this is the left hand side, and this is the right hand side of all here. I'm just gonna use the what we call coefficient comparison on both sides. Okay, for each j, okay, you know that this is the constant, the term that multiply to cos omega jt, which for each j here need to equal to this term for on the left hand side. Okay, but on the left hand side here, you know that there's some similar term like u sub j here that you can combine coefficient together and with v sub j, and that's what we did here. Okay, u sub j here, we combine coefficient that multiply u sub j in one, and this one is for v sub j, and then comparing that each have to be equal to a star j, because remember that a star j is a simplification here for all the is a parameter the amplitude of cos omega j from the right hand side function of the equation. Okay, so therefore for each j you end up here, okay, having a system of two equations. You have u sub j and v sub j here. Okay, for each j is independent of each other for a given a star j and b star j. So you can solve for u sub j and v sub j for each j, okay, easily by using what you call the Kramer's rule here. So you might remember the Kramer's rule is that we just write this equation in metric form, and the coefficient that form from the left hand side equation, okay, this is what they form is a metric form. This is for the first element. You look at the value in the bracket, okay, and then multiply u and v for each equation. This is for the first equation here. This one for u, this one for v. This is for the second equation is a coefficient. Look at based on this equation, and you find this determinants. Okay, And this one is way back for your high school mathematics. We can solve and derive this by using what we call the Kramer's rule. Look at here that, okay, if I want to find the determinants of 2 by 2 metric, size 2 by 2, I'm just use this diagonal element multiply to each other, which is the same value. So once they multiply to each other, it becomes square. And then minus, okay, minus these two multiply to each other. You can see that these two terms are almost the same, except that if you reverse the sign here, it becomes c minus a omega j squared, and you have minus psi over here. So it's the same value, but these two value is the same, but just different sign. Okay, and you remember the classic formula to find determinants of this one. You get you use the diagonal multiply to each other, and then you minus. Since this one is a minus, okay, so it become plus, and you already reverse the sign here. See the minus sign, the term in the bracket will be exactly the same. So you just use this and then multiply to each other. Okay. I think I forgot the square here. Okay, the first term should have some square also. Okay, I forgot this one. You remember c minus a times omega j square all together have to. You're missing another square. Okay. Oh, no. Um. Uh, yeah. You're missing another. I'm missing the square here. That's correct. So this one has to be c minus a times omega j square, or in the bracket you have and add another square. Okay, you need square here. Yeah. So because you need this term multiplied to this term, and then subtraction from this the multiplication from the diagonal element. Okay. So we're gonna call this one theta 0j. Okay, and then if you want to find u sub j here for each j, you just replace the right hand side vector here of a sub a star j and b star j in the first column or from the previous determinants metric that you found for the delta 0j. You put this one in the first column and keep the second one the same and find the determinants. Okay, certainly this is already very easy. This one multiply to this one, and then minus this one multiply to this one. This one we're gonna about delta 1j. And certainly to find v sub j here, okay, you just put a sub j and b star j here in the second column corresponding with v sub j, and keep the o from the original that metric that find delta 0j in the first one, and find the determinants here. And straightforward substitution, you have this multiply to this, and then multiply minus a star j. This one should be a star. Okay, I forgot to write. This should be a star. Okay, this one a star. Okay, but a is the same. Okay, a omega j is the same, but this one should be a star. Okay, so there are two mistakes in this equation. Okay, the first one here with this bracket of c minus a times omega j square. All of this need to be square. Okay, when you apply it to have square here. And the second one is right here is that the term a here, a sub j here. Okay, the a sub j here need to be a star j, just like this one is minus b star j. This one should be a star j times a times omega j square minus c. Okay, once you make correction of this, this is the exact formula for the what we call the Kramer's rule. Okay, you have this one. Okay, the fraction between this delta 1j over delta 0j is u sub j, and delta 2j over delta 0j is v sub j, where j is equal 1, 2, 3 to m. Okay, so that finish deriving the formula. Actually, we use a similar technique that we taught to you before. Okay, that is just a comparison of coefficient. Okay, from both left hand side and the right hand side. Okay, Okay, so this is gonna be, since you know that this is u sub j, this is v sub j from this one, you know now the general form for, you already show illustrate all the general form for I sub pt. Okay, the particular solution over t. It doesn't matter what kind of condition for complementary solution, I a particular solution will be in this form. And next, okay, this is a more tedious part, is that you need to study to analyze each case of complementary solution. Like you know that the complementary solution we show you before, that there are four cases, okay, in this. Suppose that we start with the case number one, okay. Okay. Here, the case number one here, okay. And you have three initial conditions, suppose I0, I pi 0, I double pi 0. Yeah, so you just use this, and then first, okay, you substitute t is equal to 0. Once t is equal to 0, it's obvious that this is all the complementary solution are all C1 plus C2 plus Ct. But for the particular solution, you look at here. If t is equal to 0, the sign of 0 is always 0. So the second term here of j for all j is all 0. Okay, only the cos 0 is equal to 1. That's why you have a remaining term like this, summation j equal 1 to m delta 1j by divided by the delta 0j. And this one c1 plus c2 plus c3. For the second derivative, you know that the second derivative, once you find derivative for each term here, okay. I'm not gonna write it down for you, but the first term here you get s1 times c1, okay, exponent of s1 times t, plus s2 c2, okay, c sub 2 times exponent of s sub 2 times t, and so on up to the third term. And then once you substitute t is equal to 0, okay, so then you get this one, s1, s sub 1 here, the root, right, distinct root in this case, s sub 1 times c1 plus s sub 2 times c2 plus s sub 3 times c3. But then for IPT, you have to know that you have to find the first derivative also. Once you find the first derivative of IPT, you know that this cos become minus sign, and therefore this term is vanished when you evaluate when t is equal to 0. Okay, but this term sign become cos, okay, cos. Okay, and when you evaluate t is 0, this term delta 2j by delta 0j become effective. But you need to add omega j here, because once you find the derivative on the part of particular solution, when you find derivative of sine, you get cos, but you need to find derivative inside the angle also, that get the omega j. That's why you get the omega j delta 2j by delta 0j. This one. And for the second order, you know the second order, you find, once you find the first order, you get s sub 1 times c sub 1. So when you find derivative again, you put another s sub 1 multiplied to the previous coefficient, which is s sub 1 times c sub 1. It becomes s sub 1 squared times c sub 1. The same as for the second order, become s2 square times c sub 2, and then the third term is s3 sub 3 square times c sub 3. And also the right hand side function also, once you get the second derivative of first derivative become, you have to way back, you have to look at here. First derivative you have cos, and this one become cos. You know that when you substitute t is equal to 0, the sine term is already vanished. For the second order, okay, it becomes here, the coefficient here, become minus omega j square times u sub j. And cos 0 become 1, but sine term is vanished, okay. And this is the resulting, that's why the constant term for the particular solution, when you replace, when you substitute at time is equal to 0 is here. Summation j equal to 1, it becomes minus omega j square delta 1j, because divided by, this one is according to this parameter here. Okay, but you know that this parameter become certainly in our sense is a value of u sub j and v sub j. Okay, in this one is not complete yet until you find the relationship here of u sub j and v sub j in this form that related to the previous parameter for all j. Okay, so this one get. So our job not finished yet, because in this case you have three coefficients c1, c2, 3c, and this one is a constant value. Okay, so this is the amplitude I can evaluate. You can move it to the right hand side, and then you can see that we can end up having to solve just like this one. Suppose I say r sub 1 is this term, r sub 2 is minus, r sub 3 is a plus. This one is coming when you move this term to the right hand side. This one is like minus r sub 1, minus r sub 2, and then minus r sub 3 when you move in the right hand side. So this one become a minus sign. When move to the other side, this one already minus sign. When move the other side, become the positive sign. And that's the result of this r sub 1, r sub 2, r sub 3. And this one, the remaining left hand side, okay, here, which is, sorry, where did I go here? Okay, okay. When you have here, it become only in this form, c1 plus c2 plus c3, which is here, right? And this one, s1 times c1 s plus s2 sub 2 times c sub 2 plus s sub 3 times c sub 3 is this one, coefficient here, multiply here. And the third one is according to this one. The third for the third, you get here, and you get c sub 1, c sub 2, c sub, in the metric form. The reason I write in metric form is that so we can apply Kramer's rule again, okay? To find Kramer's rule about this, okay? You get determinant of 3 by 3. Okay, I'm not gonna tell you how to do it, but it's an old high school mathematics, if you might remember. This is the resulting of finding the determinant of 3 by 3. Okay, and I believe that in the first freshman year you familiar with the formula. Okay, so this is the resulting and the rearrangement of the term. So this is the determinants of the original matrix here. Okay, and this is, I already arranged the term. We call this the resulting is as theta 0 sub 0. And you know that if you want to find c sub 1, c sub 2, c sub 3, you just put this right hand side vector here. Okay, to suppose you want to find c sub 1, you find the determinants of this matrix by replacing this vector to the first column. For c sub 2, you replacing this vector to the second column, and the third c sub 3 replacing this to the third column. Okay, and find the determinants of the resulting matrix, and then you can get the ratio. Okay, use that as the ratio. Find the ratio with theta 0 divided by theta 0 in other words. Okay, you get the general form to find c sub 1, c sub 2, c sub 3. And that's what we did here. Okay, you see, you place r sub 1, r sub 2, r sub 3 in the first column, just keep the remaining metric, and then you find determinants, and then rearrangement the term you get, we call it theta 1, and this one also replace in the second column, this one in the third column, and find the resulting and rearrange the term. Okay, this I already rearranged the term for theta 1 here, but theta 2 will just leave it here. So theta 2 didn't rearrange anything. But the resulting is that it will be here. This is according to Kramer's rule, okay, from very fundamental matrix theory here. C sub 1 is theta 1 divided by theta 0. C sub 2 is theta 2 divided by theta 0. And c sub 3 is theta 3 divided by theta 0. Okay, so now you know that the problem in the first case is almost finished. Okay, here. Okay, we finish here. Because now if you look back, okay, you'll be able to find it, a function of I over t, as a complementary solution. You know complement, this one complementary in case 1 is here, and you know the particular solution here. Okay, and you'll be able to find with three initial condition, you get this to find, you get the formula to find this one, C sub 1, C sub 2, C sub 3. Okay, for given data, problem data. Okay, so then this is just finish only one case of case 1. Remember that how many cases do we have in there here? We still have this one, 3 more cases here to find C sub 1, C sub 2, C sub 3. We only did one case, so you see have 2, 3, 4. Okay, plenty of work for you to work and exercise on this problem. Okay, and also if you look at the uh, recommended homework here, okay, that we put it on here, we say that thirdly you want to derive the formula of C sub 1, C sub 2, C sub 3 for other case, the second case, third case, and fourth case. And also we going back that this is the first example we analyze when your right hand side function is in the sinusoid combination of sinusoidal form, right? Remember that we assume here, we assume that function of E over T is in this form. And if you might remember that it was a homework here, okay, here, okay, for 2.1 also, when you apply for the classical spring problem here, a sub j cos omega t, just with the same format here. Suppose force function is in the sinusoidal form. Okay, so we already did illustrate to you how to handle this. Okay, but we apply in a more difficult situation also in the third order system. So to finish it up here in this problem, you have to check all the four case finish. And then when you go back the problem, you remember that from the previous clip, except the first two example, we always, the first three example, we always assume that when your right hand function is the polynomial order R here. Okay, so it's still open that if we suppose your ET is not the summation of the sinusoidal function, okay, it becomes the polynomial order R, okay. Certainly in this case, you're going to end up having 4 cases also, okay. And we have to derive all the possible formula for function of I over T. So plenty of work that you can exercise yourself based on the knowledge that I already tell you, okay, from the start here. Okay, so I'm gonna finishing up this part here. Okay, and we're gonna take a look at another example, or maybe just a second example of what we call the higher order system. In this one, it becomes the mechanical system here. The two of them I think that is the double of the previous from last clip at the end of last clip exam, because just only standalone of the spring, damper, and mass. Okay, it's a second order system, but once you have two of them connected to each other, you might guess in advance that the resulting model can be what we call the fourth order system. Okay, but that's not what we're going to cover from in this clip. Okay, that will be illustrate in the next coming clip. Okay, so from before the end of this clip, okay, let me remind you that okay, the information in this clip have not finishing the problem yet. Okay, with this 2 homework, okay, for you to exercise. Okay, see you in the next clip. Okay.